Welcome to the viewers. Today we start a new chapter called Classical Mechanics. It's a very important topic in the aspect of the different types of particles of then study of their motions, and especially already we are endowed with new things of the concept of Lagrangian mechanics and then at last Hamiltonian mechanics. So we have some preliminary idea. Before started, we discuss one things. Already, if we are knowing that we assume the Newton's three laws of motions. First law is everybody continues in its states of rest or uniform motion in a straight line, except in so far as it be compelled by external forces to change that state. It is the first law. And second law is the rate of change of momentum is proportional to the impressed force and takes place in the directions in which the force acts. It is the second law. And to every action there is an equal and opposite reaction. It is called third law. And all these law we already known. And the first law that speaks of a class of special frames which are called unaccelerated, and each of them moves with a constant velocity with respect to any other one. It is difficult to give general and broad definitions of the inertial frame. A commonly accepted one goes as follows: a frame that is fixed relative to average position of a fixed charge or that moves in a constant velocity is called an inertial frame. And already we are assuming that it's happen in inertial frame, and frame which is not inertial is called non-inertial frame. Thus rotating frame of frames undergoes accelerations are to be treated as non-inertial frame. And for short scales, the planet's Earth serves as an approximate inertial frame. However, strictly speaking, that's any reference frame attached to the Earth has to be rotating and hence ceases to be inertial. Now later we know everything for the Coriolis force and different things. And this is all these have the preliminary idea, and now we skip the matter into the conservative forces. We have given some idea of the conservative forces. Conservative forces have a natural occurrence in classical mechanics, and the conservative forces are such the work done by them as the system moves in the configuration to others depend only upon the inertial and final coordinates of the particles. Then conservative forces may be distinguished as one of the following features. Which features are there? The features of conservative force. Number one is the WD, that means work done by the force is independent of path. By the second features, if we consider the components of the Cartesian coordinates, the Cartesian component fx, fy, fz of the force F that means if we are saying it fxi plus fyj plus fzk, for ij kth component fx, fy and fz k of force F. Then here is the formations. Which formation is this? It is a differential, that is fx dx plus fy dy plus fz dz is an exact differential. That means it is called df, exact differential of f. That means next formations is number 4. F is only the positions of a functions. That means f is only a function of position. That means if we take it as a vector, that is vector valued function, and curl f, that means del cross f or curl f, that's a vector concept, it will be 0. That is a null vector. A potential function v exists that has a definite value at each point. Next things is also very important. Number 6. That is, if we called T as kinetic energy or K as kinetic energy, whatever notation we used, if we notation is uses T or T1, if T1 with the kinetic energy, because we can't mislead with the term periodic time, that's why if we giving it T1, and we make V as a make V as an energy function V, that's a potential energy V. Then if we taking as V1 potential energy, that will be always constant, where T1 is kinetic energy, that is Ke, and V1 is potential energy function, that is Pe, potential energy function. Now from the conditions force, that is curl F0, that's we can write f is a gradient of some scalar function. It is a property of vector valued function, that is a property of vector calculus. If we say curl F0, then we declared this function which we operates the curl, this function is the gradient of some scalar valued function. Since the gradient points towards the direction of increasing potential and forces cause the system moves towards the lower potential, so a negative sign is chosen. That we have done in vector calculus, and it is an interesting property of vector calculus and physics. So you can write it v is equal to minus of gradient v, this gradient, okay, this delta, that can be written as, it is the operator I del x plus j del y plus k del z, that is operated. Here in the earlier stages where curl F is 0, also del operator will same. In other words, the force is negative gradient of some potential V So one dimension we can simply have if we taking it. That means if we are breaking the component, that is fxi plus fyj plus fzk, that will be equals to minus of I del del xi plus del del yj plus del del zk with, sorry, if we are writing in this way, minus of I del del x plus j del del y plus k del del z operated with v, that is a scalar potential function, then we can take it as minus of, breaking it as I del v del x plus j del v del y plus k del v del z. And if we are comparing both of the side, we can get easily fx equals to minus, that's partial derivative is total derivatives for the particular function, particular component, that is called dv dx. Similarly for fy component, we find dv dy, and fz component we find minus of dv dz. Now if we are taking the particular valued function like fx dx or fy dy, whatever may be, if we are taking it in this way, and if we are integrating within the point integral a to b fx dx is equal to minus integral a to b dv dx, that will be integral a to b dv. So it will be clearly as function of property of integration, that is minus of dv and dA. If we are taking as the differences, and it is reverse delta, it's happened sometimes, its minus is totally changes, that is a total reverse delta sign, difference signs. And these signs already we study difference of equation. Therefore we have the following principle, that work done on the system positive increases potential energy, and the work done by the system negative work decreases the potential energy. Now that's we learned just previously earlier the constancy of the angular momentum in the central force problem. For the orbital problem plane, it is a property that's already we have in 3 dimensions and rigorous. That means in the orbital plane, if we are calling it the equations, which equation forming orbital plane, and assuming we have the prerequisite conception about the plane, so let us consider the equations of the orbital plane. The orbital plane L dot r equals to 0, that is a scalar, is the one on which the motion lies, and which is normal to the plane. We already know from the vector theory concept the condition of the normality, that is L dot r equals to 0, and the one which the motion lies, and their dot product already 0, that means the motion is normal to the plane. And if we assume that mod of L is non-zero, If r theta be the coordinates, that is polar coordinate of the orbital plane with respect to the fixed origin, then Newton's law says there are the two motions, radial motion and cross radial motion. We already studied in central force problem of earlier mechanics. That is called the central force problem of kinematics, especially for the earlier mechanics. In Newton's second law, if we recall it, that is m into radial direction and cross radial direction. For Newton's second law, with respect to the fixed origin, r double dot d2r dt2, that is m into d2r actually just a minute, m into d2r dt2 minus r into d theta dt whole square is equal to this vector f. That's the radial directions, or the vectorial radius vectors, and theta be the vectorial angle. It's clear. And in the cross radial direction, we know m into 1 by r ddt of r square theta dot. That means if we are breaking it, r into theta double dot d2 theta dt2 plus 2 dr dt d theta dt, their value will be 0. In the second equations, we already modify from the second equation what we find. From second equation, 1 by r dd t of m r square theta dot equals to 0, and that pointing the constancy of the angular momentum. If we take L is equal to m r square theta dot, that's the angular momentum, because we already know omega is d theta dt in the rotational motion with respect to time, angular momentum with respect to time. And from the first equations, we write that fr, if f be the function of r, that will be minus dv dr. Then we can write it mr double dot equals to minus, and if eliminating theta, it will be reduces as ddt of L square into 2mr square function of r. If we eliminating theta and after reducing, we are getting this result. If we take equation number 1, and this result is a typical equation of motion one dimensions on the half line, that is 0 to r under infinity, and influenced by the effective potential, if we are taking is u LR is equal to L square by 2mr square plus VR. And actually which, by what we get it? By eliminating theta from these two equations, and we replace L is equal to mr square theta in this way. From the second equation, mr square theta will be L. We derive from the second equations, and we can get it here, theta dot equals to L by mr square. And if we are substituting it in the first equations, we get some result. Clear? Here it is m r square theta dot, and fr is put as minus dv dr. Already this will be L, and from the first equations, just for the note, this mr square theta dot, that will be substituted in the first equations. That means theta dot equals to L by mr square. Put in mr double dot minus r theta dot square equals to f. So here it is obvious result. That means mr double dot minus mr theta dot square plus f. F means minus dv dr. Now if we are putting mr double dot minus mr theta dot square will be L square by m square r to the power 4 is equal to minus dv dr. It is obvious and clear. Then mr double dot equals to minus L square by mr cube is equal to minus dv dr. If we taking in the another side, that is L square by mr cube plus dv dr. Now taking and including in any operator, that is minus, if we taking minus ddr of L square by 2m r square plus, it is simply v or vr. V is the function of r in this way. How is it possible? If we are breaking the bracket, it is very clear that L square by the differentiation rule by twice m, and if we are taking it minus 2 by r cube, this 2 will be cancelled and minus sign will be plus sign, minus dv dr. So that will be L square by mr cube plus dv dr. So it is clear and obvious result from the background, and by some manipulations, how is it possible? We can give the rigorous treatment. So finally we find ULR equals to finally we find AMR double dot equals to this, and taking ULR is equal to this result, and the first term in the side that can looked upon coming from the centrifugal force whose magnitude is L square by mr cube. Now the total time is constant. So total time is given by there is a magnitude, okay, L square by mr cube is a centrifugal force whose magnitude is L square by mr cube. Now the total time is constant is given by E is equal to half of m v square plus vr, that is half of m r dot square plus ULR. Now laterally we discuss few types of conservative law and continue the chapters of another different topics like D'Alembert principle, generalized coordinate system. Thank you.